Now, let's continue with section 2.1.3. You will notice at the end of example 12, what we have here on the left of the dividing line in the augmented matrix is the so-called identity matrix. Identity matrix has ones on the diagonal and zeros everywhere else. And I've mentioned how this identity matrix corresponds to the simple variables in the original equation. Because I have a 1 here in the first column that signifies x, and all the other variables are 0. I have a 1 here in the second column that signifies y. All the other variables are 0. So the identity matrix is a nice matrix to have when you're dealing with augmented matrices. Now what this says here is that for a system of linear equations, the goal of Gaussian elimination is to convert the part of the augmented matrix left of the dividing line into the identity matrix. And I hope you can see that once you've done that, you can read off the solution of the system of linear equations. Now, for many systems, it's not possible to reach the identity in the augmented matrix via Gaussian elimination. In any case, a certain version of the matrix that has a maximum number of components eliminated is said to be the row-reduced echelon form, or RREF. And we have two examples on page 13 and 14 of the text. In this example on page 13, example 13, we have this system of equations, and you might notice that the second equation is simply 2 times the first equation. So it doesn't introduce any new information. When we do this process of row operations, which corresponds to adding equations to each other, here we've written the equations as augmented matrix. Here we take 2 times the second equation minus the first equation, and we get all zeros here. All right. Now you could say this is even simpler than an identity matrix. We can't eliminate this 1 here because there's nothing to eliminate it with. But we have made this entire row full of zeros. Okay, so we really can't go any farther. This just says x plus y equals 2. Can't reduce this system anymore. Now if you think about plotting this in a plane, as we'll see later, this is a line. And in general, you do get solutions that are lines or points or generalizations of those. So here's one case where we do not get the identity matrix, but we do get something simple. Now here's an equation where we get the same thing, only this time the second equation is not 2 times the first equation, it's 2 times the first equation plus something. Here we get a system of equations where the second equation cannot be solved. So in fact, this system of equations has no solutions. Again, the form here is not the identity matrix, but we do call it RREF because we can't make it any simpler. Now, so far in our Gaussian elimination process, all we've been doing has been adding and multiplying equations. But sometimes it's necessary to exchange equations in order to obtain the identity matrix via Gaussian elimination. Now, exchanging equations in a list of equations certainly does not change the solution. And here's an example right here. Here we have two equations here. We have y equals minus 2, x plus y equals 7. The augmented matrix form is 0, 1, minus 2, 1, 1, 7. And the only way we can make this into identity matrix is move this equation with a 0 to the bottom. So we've just exchanged the two equations, but that does not change the solution set. And if we do that, we can get the identity matrix. So that's a good solution to finding our reduced row echelon form. Now, if you think back over our Gaussian elimination examples, there have been 3 types of row operations that we've used in order to perform the elimination. Here we did a row swap. Now previously we have seen adding a multiple of one row to another row. We actually see that right here. To obtain this 109, we subtracted the second row from the first row. That amounts to taking the first row plus -1 times the second row. So that's another row operation, is adding a multiple of one row to another row. The last operation is simply multiplying one row by a constant. If you look back, you'll see that there's a case, I believe, where we divided a row by 3 and replaced that row with the divided row. This gives us 3 so-called elementary row operations. The first is exchanging 2 rows. Second is multiplying any row by a non-zero constant. Third is replace any row with that row plus a multiple of some other row. 3 operations. Now, these operations are used in a systematic process or algorithm, and the steps of that algorithm are described as follows. First, you make the leftmost non-zero entry in the top row, turn that into 1 by row multiplication. You may have to exchange rows in order to do that, but typically you do this first. You then use that 1 as a pivot to eliminate everything below it, then go to the next row and make the leftmost non-zero entry into a 1, and use that 1 as a pivot to eliminate everything below and above it, and continue. So as he says here, in case the first entry in the first row is 0, you may interchange. So sometimes it may be necessary to interchange rows. All right, that's a very sketchy description, but you can look in the text. There are some video links that give examples of Gaussian elimination. And there are many videos on the web that show examples of Gaussian elimination. So if you want practice with the process, you can certainly find videos to do that. I think also that Khan Academy has videos on row elimination. So how do you know you finished? Well, when you finished, then the part of the augmented matrix to the left, well, actually the entire augmented matrix is in reduced row echelon form, and these are the characteristics of reduced row echelon form. In every row, the leftmost non-zero entry is 1 and is called a pivot. The pivot of any given row is always to the right of the pivot of the row above it. So this you call stair-step form. And the pivot is the only non-zero entry in its column. We can see a couple of examples here in the text. This is in reduced row echelon form. This is a pivot, and all other entries in that column are 0. The next pivot is to the right, and all other entries in that column are 0. The next pivot is over here. These are not pivots, but that's okay, because still the first non-zero entry in this row is 1, and all other entries in that column are equal to 0. So this is in reduced row echelon form. This is not reduced row echelon form. Why is that? Well, this pivot is fine. First non-zero entry is a 1, and all other entries are 0. Then if we go over here in the next row, the first non-zero entry should be a 1, and that's not true. Also, this non-zero entry is to the right of this one. This one is to the left of this one, so the stair-step pattern is not correct. In order to make this into REF, you'd have to exchange these 2 rows. You'd have to change this 2 to a 1, and you'd have to get rid of this entry here. And here also you can see that this one here does not have all zeros in that column. So this one does not meet the criterion for a pivot.